So yeah, as she told, I'll be touching upon the page buffer overview, which would definitely look into the what are PLSQL pages, what are PLSQL pages, and how these pages are organized, how these pages are being swapped in and out of the PLSQL memory, sorry, Postgres memory. So how it's been organized and other stuff like that. So let's start with what is buffer cache and what role it plays in PGSQL. So basically, when we've been talking about shared memory areas, right? So this is a very important shared memory area wherein the data that is being stored in physical files. I think the last session, ma'am was telling about the data restoration. All those data that's being restored, the files, the physical files that are being read from the disk and stored in the shared memory buffers. So what happens is, like, this shared memory buffer is kind of available to be used by all the PL/SQL, all the Postgres processes, and since it's all in the memory, right, it enables a quicker I/O rather than to read from the disk. And how this data is being stored, because shared memory, it's going to be very limited and the disk is kind of very large. So it kinds of has the memory, divides the memory into different pages, which is like generally of 8 KB size, and those memory pages are being pushed in and out of the shared memory. And this shared memory has an internal lookup wherein it will try to understand whether this particular page that I would need is already available in the buffer cache or not. So if it is available in the cache, it tries to use it. If it is not available, then it tries to load it from the cache, from the disk into the cache and starts using it. And on the configuration size, typically this shared memory, it's recommended to have it as 25% of the RAM size, and the default configuration is around 128 MB, like if you don't give any changes. And in the code, it's been initialized in the freelist.c file. So when we talk about page buffer, then we also know that most of the modern operating systems has a cache for all these files inside. So how these two are different? So it's basically the same. So we have a cache in the OS that will store the files, that will store the OS physical files that are being frequently used, and the same way Postgres also stores the same thing. So what happens this way? So what happens here is, like, in case of Postgres and the OS both having the same kind of cache, so what happens here is we have a double buffering mechanism. So data is both cached with the Postgres as well and on the operating system. Yeah, this is kind of an overhead that is there, but what the reason for this is, like, this kind of cache ensures portability across multiple operating systems, because not all operating systems is available for this kind of OS cache. And to avoid this double buffering, what we need to do is we need to start using a direct I/O method, wherein the data that is there on the physical files will get into the Postgres cache without even getting into the OS cache. So an attempt was made some time back, maybe around 4-5 years back, if I remember, and because of these portability issues, that was not fully merged into Postgres main branch. So with the shared memories, right? So we were mentioning about the 25% of RAM that's been stored, or 128 MB, that's a default cache. So that particular information is provided by a configuration parameter shared buffers. And if you look at the Postgres configuration, right, there is one more cache parameter which is effective cache size. How is this different, and what these things, why there are two different parameters here? So the first one is, like, for the actual physical memory that's been allocated for buffer cache, and this one is more used for computing the cost of the queries. So it says, okay, it assumes, okay, this would be my cache size for all the operations, and the cost of the query would be computed based on this size, not on the actual memory, the shared buffer size. And this one, whatever the numbers that's there here, that will not have any memory, physical memory allocations to that. And yeah, I mean, when they say cost of the memory, I mean cost of the query, so it basically says, okay, what index can be used? Can I use any index, or should I go for a sequential scan? So those kind of decisions are being taken from this parameter, whereas the other parameter, shared buffers, it's actually is the amount of memory that's been allocated, and that would be the memory that would be used by Postgres for reading the data from the physical files. So what's the physical page size? So we talked about shared memory and shared memory pages. So what is the size of these pages? So page size is basically around 8 KB. So let's say how it works is, like, say if you are allocating 128 MB of space memory in the shared buffer, so that would be converted into 8 KB blocks, and those 8 KB blocks would be the shared buffer. And when you do a lookup, that lookup will get into look for these kind of 8 KB blocks. And this can be changed based on our need, but there is a compile time parameter, and that once the Postgres is compiled, it cannot be changed again. That would result in data corruption. So what is stored in the page buffer? So in the pages, generally it tries to store all the data, which basically data in form of tables and index. So every index and every in a table that has been stored in Postgres is converted into this kind of 8 KB blocks and stored in multiple pages. So a page can span across multiple pages. A table can span across multiple pages. Similarly, an index can span across multiple. And when we try to do a data retrieval, when we try to do a retrieval, let's say index. When we do an index, index has the information about the page ID, and it goes and gets the exact page where the data is located, and that page is being loaded into the page buffer again for further processing. So let's go a little deeper into the pages, like let's see how this page is organized. So as for any data, right, it has a structure of header followed by the data. So initially it starts with the page header, which is like 25 bytes long, and followed by the data storage, and finally they have a special space. So this special space is used for storing index related information. Basically for any kind of table data, this special space is kind of mostly empty, and for index, yeah, it has a lot of information about the index. Like it also stores, in case of, let's say in case of B-tree index, it stores the next and the previous record childs, the sibling data. So by the way, it can try to access the information much faster. And when we come into the data storage, right? So data storage is again divided into two parts. One is the pointers to the place where the actual tuple data is stored, basically the row data is stored, and the actual data. So how it's organized is like with the first tuple data that's been stored. I mean, it's not the first row, it's the first tuple data that is stored within the page is stored immediately after the header, and the corresponding data is stored just before the special space. So which means the free space available will be there in the middle, and the data can be stored, the pointers for data can be increased from the beginning, and the actual data would be stored towards the end in the reverse order. So first row pointer would be there immediately after the header, and the first row data would be there in the just before the special space. Second row would be just before, just after the first data, and similarly this way. And what that page header data contains. So when we look at the page header data, right, as I told, it's like 24 byte long page header data, and the first 8 bytes it contains the log sequence number from the val record, so that it will know where exactly this page has been available in the val. And next is a checksum. Checksum is something which is enabled, which is generally filled when the checksum parameter is enabled, otherwise it is left empty. But in case if the checksum parameter is enabled, that means the data would be taken, there would be a checksum that would be computed and will be checked against that. That means there would be some kind of a performance impact on enabling the checksum. And the next 2 bytes would be flags, and the next one, which is the fourth one, would be a pointer to the lower, which is a PD lower, which is like to point to the start of the free space, and the upper would be the end of the free space, which is basically the beginning of the tuple data. So lower would be the place where the next record's data pointer would be written, and upper would be the place where the next record's data would be actually written. And next comes the special, which contains the address of the location, the start of the page space, the special space. And next comes the page size version. So page size version will have a number which says, okay, at what Postgres version this page has been created. So it typically the current page size version is 4, which is from 8.3 it is made as 4. And 8.3 and 8.2 and 8.1 has 3, 8.0 has 2, and anything before 8.0 until 7.3 has 1, and finally anything before 7.3 Postgres version will be stored as 0. And the final parameter is the transaction ID, which says, okay, the Xmax for the current page, which is typically used to understand whether the data can be pruned or not. So if there are too many of changes, the data has to be written into val and it can be removed. That information is being stored in the is being taken from the transaction ID that's stored here in this header. So how this buffer, we spoke about page buffer, the role and the structure of it, and how it is actually used when we do a query. So we will see with some examples here. So this is after the initial start of the database. The shared buffer size that's been given is 128 MB for our understanding, and so it says, okay, the parameter shows shared buffers is 128 MB, and we have a PG buffer cache extension that is available that will actually give us more details about the buffer, the current state of the buffer. So when I look at the count of star, which says 16,384, which is like of 8 KB blocks, which will translate into 128 MB together. And I am also taking an example for a table which says cast, and that table has 10632 pages on the disk IO as of now. And the next query, which actually does little more detailing on the PG buffer cache, it also says how many buffers are being allocated for this particular table in the buffer. So here there are no rows, which means for this particular table there are no rows allocated in the PG buffer cache. But PG buffer cache by default will have some data that's used for PG catalog and other metadata related information to start with. Now let's execute a simple query with the index scan. So this table has a primary key index which is on the movie ID, and I am doing a query exactly on the movie ID, which will invoke the index scan. And if you look at the data, right, it says buffer, it says shared hit 4 and read 14. So which means there are 14 buffer information that's been read. The 14 pages are read from the disk IO into the buffer cache, and that information is being reused. And there's a separate parameter called the shared hit, which means out of this 14 pages that's been read, it's been reused 4 times after the cache has been loaded. And it has around 10 rows that's been, it has around 16 rows that's been fetched, which means like 14 pages are being read for this 16 rows, and this 16 rows would span across 18 queries. 18 times the buffer has been looked out for, and 14 times the new data has been pushed inside, and 4 times that it's kind of reused. And we go to the next stage where it says how many buffers are actually loaded into the buffer. So earlier when we saw for the same query, the output was 0 rows. So now when we look at it, the same table in the namespace public and the table called cache, it has around 10 buffers that's been loaded, and since it also looked at the primary key, the index is also a data that's stored in disk IO and that's been loaded inside the buffer. So it has taken 5 index pages that's been used. So it's like 10 rows, 10 pages of data and 5 pages of index that's been used for this particular query, and for the output of 16 rows. So what happens when I try to re-execute the query? So when we say that the 10 pages that are required for the data is being stored now, and when I try to re-execute query, it tries to look out for the pages that are required, and all the pages that are required are already there in the page buffer. So which means there is nothing that's been read from the data, and that would improve the time for which the response time for the query, because there is no data that's been read from the disk into the buffer. So that time is saved, and everything that's been, because everything has been read from the buffer itself. And you can see that there are no pages there. It's just a shared hit. It's always 15, and all the 15 pages that are required are already there in the buffer. So when I try to run the query again, when you try to run the query multiple times, you can also see that the execution time is still optimized, and there are no further reads from the disk IO. So this is for the index and the thing. So what happens when I try to read the data, read more data into the pages? So now I do a select star from the table, which means I will not be using any index. I will be directly going with the sequential scan, which means all the pages that will be read from the disk IO into the table. So if you remember, we saw around 10,300 pages for the cache, right? So if you look at here, so there are 9 pages that are shared, that is already available in the cache, has been used, and rest of the pages are all reloaded. So out of the 10,600 and odd pages that are there earlier, now it's loaded for 10,000 pages. 10,623 pages were loaded from disk IO into the memory, and 9 of them were reused. And if you look at the same query, so how many buffers are currently being used, we can still say that there are only 42 buffers that's been used, which means all the data that's been read, the 10,623 pages that's been read from the disk IO, are being swapped within this 42 entries in the buffer cache. The reason why that's been that way, we will probably get little more detail when you look at the eviction algorithm, how the algorithm works, but which means that it was able to get the entire set of data with just 42 buffers here, and rest of the data, whatever is there, it's all been unused. Again, similarly, what happens when I run the same query multiple times? So is it going to read all the 10,623 records again? No. So what happens is, when it tries to read the data, now if you look at the next section, it says shared hit is 41, which means of the 42 buffers, 41 buffers are being reused, and rest of the pages were loaded into the memory. So 10,591 pages were loaded into the memory. And if I re-execute the query one more time, you can say that the shared memory hit is 73, which means like 73 buffers are being used, which is there in the memory, and rest of the pages are being read. So what happens is when we try to execute the query again and again, which means the more number of times the query gets executed, the cache gets built accordingly. So the general behavior of the database improves as and when the database runs for longer time, and with the same type of queries on the same tables queries are being executed on the same table. So when the cache is built properly, the data, you will be getting a proper response time, and it takes time to build the cache depending on the queries that's been executed. So now let's look into the buffer management, how this buffer is being managed. So buffer management, we'll look at two things. One is the buffer lookup, wherein we saw that 42 queries were the tables were cache entries were there, and those 42 were reused, and only the rest of the data that got loaded into the memory. So how that happens is like there's a buffer lookup which says which maintains the lookup hash table for all the entries in the buffer. And the next one is the buffer replacement. So the buffers are getting replaced again. So when we looked at the entry, even though we had read around 10,000 entry, only 42 buffers were kind of used. So how it works is it uses a clock sweep algorithm to replace the buffers. We'll go into the clock sweep algorithm later, and it also has a counter called usage counter, which actually tracks the number of times that particular page has been used. So does it mean like if the particular page has been used for almost every query for 100 times, will the usage counter would be more? No. So this usage counter is kind of fixed at 5, which means the usage counter can the page, even though the page is being used multiple times, the maximum value it can store is only 5. And this is again a compile time parameter. It can be increased or reduced based on our requirement. So how the buffer is being allocated? So the buffer, let's assume that I need a buffer for putting into the cache. So I'm looking into the lookup table. So if the buffer is found well within the table, so what happens is it increments the pin count and the usage count. There's some, I missed the pin count. So when we talk about pin count, right? So what happens? So why is there a pin count? Pin count means this particular page is currently being used by some of the query for any of the processing, which means anything that has any buffer page which has a non-zero pin count cannot be removed from the buffer cache, because that's been currently used across, by any of the query. It doesn't mean that my session is being used. This buffer cache is kind of shared across all the sessions. So I may not be using the same page, but some other query somewhere else might be using it. Some other application, some other query might be using the same page. So so it increments the pin count here when I try to load into the, because there is a use and I'm going to use that page. And it also increments the usage count. So to understand, this particular page is being used more recently. So I'm just, if the user count is 0 or 1, it increments by 1 item. And if it is max at 5, then it doesn't increment it. It leaves it that way. And it returns the page into the, loads the page into the application. And for example, if it is not found, then comes actual physical read from the IO. So how it is being read? So the data is being read, let's assume it's being read somewhere, and how that is being put into the memory. It goes and checks in a place called a free list. So this free list is a list of free pages that are available currently on the system, on the instance. So what happens when this free list would be populated? So the free list could be populated when you use a DML statement like drop table or truncate or drop database. So which means, let's say I'm doing a drop table statement. Whatever the table data that's been already stored regarding the table and the index, those pages are all kind of unused. It is not going to be used. So those type of pages would be added into the free list, and this would be looked at the first place, and it would be used for loading the fresh data. So let's say I am not able to find anything on the free list also. Then I have to remove one page that is already available in the buffer, and I need to load the fresh page. So it tries to find a victim. We'll look at the clock sweep algorithm to see how the victim is being found. So once the victim is found, so which means okay, I'm going to move this page out of the cache. So what it says is it checks for the dirty bit. So if the page is dirty, which means there is some operation that has happened into the page after the page has been loaded. So that means it gets that page and writes into the wall, and then it reads a fresh block into the buffer, the particular buffer entry. And it also increments the ref count like earlier, like pin count and the usage count. So any questions until this point? Okay. So now we'll see how this clock sweep algorithm works to find the victim. So I have a list of pages, and I don't know what page to be needs to be evicted. So I need to find a page now. I need to move that page out into. So it is kind of a loop, and it will be starting the entry, lookup entry from any random place, because this particular page buffer is a kind of a circular array, which means the moment you reach the last item in the array, it automatically goes into the first item in the next. So it can be started from any random place, any random item, and can start looking out for it. So what happens is it picks up some random item which is pointed to next victim, let's say, and it checks if the pin count is 0, or if the pin count is more than 0, that means that page has been currently used into the memory. If the page has been used, it cannot do anything, it just goes to the next item in the list. So it just moves into the next item. It says okay, to find if it reaches the last element, it goes to the first element in the array, and it tries to get the next element, and if at all it gets the next element, and it goes into, it also checks the user pin count. If the pin count is non-zero, which means pin count is 0, that means the page can be swapped out, and that comes in, and it checks the usage count. So you remember we saw the usage count would be max of 5. So it just tries to reduce the usage count from whatever it is and see if the usage count is 0. If the usage count is 0, then it makes okay, it understand okay, this could be a probable victim, and it moves, it gets it. Or let's assume that if a page is not having a non-zero, usage count is more than 2. So what happens? It reduces the usage count by 1, and it says okay, the usage count is currently 2. It's initially 2, and it reduces by 1, so the user count is 1 again. So it seems that okay, this particular page is kind of been recently used, and then it moves to the next page in the next item in the list. So here what happens is immediately if it is decremented, and immediately it is checked for the usage. The reason why it is done this way is that there is a chance that if I incremented it 0 and I go back and come from in the next limit, right? So there is a chance that that page may be reused by some other query. So to avoid that condition scenario, so what it does is it reduces the usage count and checks for the 0 entry immediately. So what happens when it tries to do a entire scan, and there it cannot find any pages wherein usage count is more than 0, or the pin count is more than 0. So in that case, there are only two situations possible. One is the buffer space whatever we have allocated is not enough, and that needs to be increased, or if it cannot be increased or anything, that means the database is kind of overloaded, and we have to make sure that the load on the database has to be reduced. So again, so one more thing here is like when we say that usage count is maximum set to 5, which means any entry that has the data, right? So it can stay for only 5 times in the memory. If the usage count is, if it is not pinned, which means it's not being currently used, any page can be there in the memory only for the max of 5 checks. In the 6th check, it automatically becomes 0 and that page will be swapped out. So it kind of makes sure that we don't get into this kind of out of buffer situation more often. So we'll go through this algorithms little deeper. So what happens is when you choose a next victim, right? So when you choose a next victim, so we see that let's say it starts from the second element in the list. So it says, okay, pin count is 0. I can use this page to swap out, and it checks for the usage count. Usage count is non-zero. So it tries to reduce it by 1, which means the usage count is becoming 1, and it again checks if it's a usage count is 0. So since the usage count is 1 here in this case, and it cannot be evicted, so it moves into the next item in the list, which is the next one. So there the usage count is already 1. So when it tries to reduce the usage count by 1, so the usage naturally becomes 0, and that page would be treated as a next victim, as a victim, and it would be moved into the new fresh page would be moved into that location. And how do we monitor buffer cache? I think the second one, the PG buffer cache thing, is what we saw earlier, wherein we saw the buffer data, right? So it has a lot of information on the buffer, and it typically has 1 row per buffer entry in the shared buffers. So if there are around 16,000 entries in the buffer, then the PG buffer cache will have 16,000 rows there. So each buffer will say, okay, what table data that has what file number, see what namespace, what table, what file number where the data is residing. So all those information will be available in the PG buffer cache entry, and these are kind of real-time data entries like what we saw earlier. So that means when we start using this entry, there might be a small impact on the performance as well. And with PG16, we have one more view called PG stat.io, which gives more information about it. But this is not a real-time entry. It's just that information, kind of a stats information that with which we can understand a few things. So there are 2 fields that I particularly look into. One is on the hits and the evictions for the buffer. So for the shared buffer, right, the number of times the page is found onto the shared buffer is the hits count column, and number of times a page is evicted out of the buffer is the evictions column, which means if there are high evictions, that means the page is kind of getting swapped more often, and there's a need for us to increase the buffer cache. And if there are more hits, which means the cache is right enough for loading all the data into the memory, all the data, and we are able to manage, and the database is kind of performing optimally in terms of buffer information. So yeah, pretty much that's where. Any other questions? Yes.
How does the effective cache size affect the query plan? Can you elaborate on that?
So effective cache size is a parameter when we do a query plan, right? So it takes the effective cache to see how much buffers can be allocated for this particular query. So let's say I need 100 buffers for this particular query, and in the effective cache it will be able to identify whether I can have all the 100 buffers here.
But effective cache size is essentially the OS cache, right?
It's not the OS cache. It's also the shared buffer plus the OS cache and all the details on that, and that's used whether to see whether index scan is required or should I go for a sequential scan. So if by cost estimation, right, if it sees that with effective cache, if there are not enough buffers, then automatically even the index is already available, it directly goes for a sequential scan. Maybe I am not able to hear you.
Okay. So during the query run, if there is a page which theory can use, but it is a dirty because there are some changes in the page.
So when
It
the
is swapped with the
no, dirty pages can be swapped. So what happens is when it identifies a victim and if it finds the page is dirty, it writes that page into the val entry and then it goes ahead with the swapping. If the page is non-dirty, then there is no need for writing that page into the val.
it will swap and then it will again read.
It will swap automatically without writing into the val. So if you look at here, so if V is dirty, it immediately writes the page directly into the val records and then it goes with the new set of data because the data is whatever the data is already been stored in the val. Pardon me, sir?
Does this pin count and usage count both need to be 0 before it evict the page from the memory?
So pin count has to be 0 and usage count can be 1 also. So when the usage count is 1, which means it immediately reduces the usage count and checks for it, it automatically becomes 0 and it does the check.
Any more questions?
Okay.
Yeah, actually. So during buffer unlock, they will evict the buffer, right?
Yeah.
During that time, flush buffer will be happening. Flush buffer dirty API will be called to flush only the buffer, right? I don't think so. As far as I checked last time, there is no wall being wall is not being flushed actually. Only the page will be flushed. The dirty page will be flushed, right?
No.
During the eviction.
Before the dirty page gets flushed into the right, if the page is dirty, it actually writes into the wall.
It's not wall, right? Page is getting written to the disk. The wall is not written here at this moment.
No, page doesn't. Okay, when you say page gets written into the disk, it initially goes into the wall, and then the background process is the one that gets the page written into the actual disk.
No, for wall, let's say if you are inserting a row into a table, for that particular page, if the change is being done, then only the wall related to that insert will go into the disk. After that, the page will go. In this case, we didn't do any change at all. We are just
if you don't do any change, then the page will not be dirty. Only if some change has been happened after the page has been loaded into the cache,
yeah,
that means the page is dirty.
Yeah, exactly. The dirty when we do insert, we did the change modification on the page, so we call it as dirty.
Yeah.
So when the insert happened at that point of time in the heap underscore insert API, the xlog insert happened. At that point, the wall will be flushed. After that, during the let's say we have 16k buffer blocks, right? By default, 16,000 something. So if every 16,000 blocks are filled, we'll then go for the clock sweep algorithm for checking one by one. If every page is let's say dirty, at this point of time, only the page gets flushed.
No, as far as I remember, it doesn't check after it goes into it gets filled all the 16,000 records. I mean 16,000 elements in the buffer cache. So it starts with the clock sweep, and if it's the usage count and pin count is non-zero, it actually swaps it.
Yeah. The clock sweep will go through all the 16,000. That's what I meant to say.
I'm not getting your point here.
I will talk.
Okay, fine, yeah.
Thank you.